Hello, I'm DTM Master's Course Donghyun-gu, and today I will present about patent image retrieval using transformer-based deep metric learning. Contents are followed. Patent search is essential for assessing novelty and inventive steps, but traditionally relies on text-based methods such as keywords, IPC, and CPC. However, text-based retrieval cannot fully capture invention essence, particularly in fields where shape-based features are critical. Patent drawings provide essential structure details but are abstracts and monochromes, making direct application of natural image retrieval methods difficult. This study proposed a novel architecture combining transformer-based deep learning and arc-based metric learning to improve patent drawing retrieval performance. It leveraged the large-scale deep patents dataset to quantitatively validate performance improvements and achieve SOTA results. CNN-based image retrieval shows higher performance than conventional local features-based method. Re-examined dataset annotations and compared local feature-based and versus CNN-based approaches, showing that CNN-based global descriptors improve performance. The GEM pooling method generalized average and max pooling with trainable parameters to improve image retrieval performance. CMS and triplet network architectures have been widely applied in recent CNN-based image retrieval tasks. The limitations of text and classification-based approaches is that patent search have long relied on text and classification-based approaches such as keywords, IPC, and CPC. However, in cutting-edge technologies, classification accuracy is far from perfect, failing to adequately reflect the essence of inventions. Professional patent research can grasp the essence of inventions and select appropriate tools, whereas AI-based automatic classifications often misses the invention's core. This often results on AI-based methods assigning incorrect IPC codes, leading to practical inconvenience in patent search tasks. A CNN-based study performed classifications of 8 IPC types and 9 drawing types simultaneously, but the image representations was tied to existing classifications, leading to sparse representations. Since all drawings within the same applications were assigned the same IPC level, issues of classifications omissions and sparse representation persisted. Uh, Berta used VAE to represent patent drawing, which was adequate in limit domains like footwear, but inadequate for broader technical fields. Kroll applied the deep patent dataset with resonant 50 and triplet laws, showing that patent drawing retrieval is possible, but the low MAP performance was insufficient for practical use. The triplet methods optimize the margin-based laws over anchor positive-negative embedding to pull positives closer and push negative further. The paper presents triplet laws as followed and computed by a shared weights network over two distance. As a limitation, it handles only one positive and one negative pair at a time, making negative uses inefficient when negatives vastly outnumber positive. InfoNCE is a contrastive loss widely used in self-supervised learning. It trains many negatives per anchor positive within a batch. So larger batches improve sampling quality and learning stability. The paper gives the laws as followed and categorizes it as a cross-entropy based methods that address triplets with negative usage limitation. ArcFace achieves metric learning by augmenting softmax cross-entropy laws with normalizations of weights and features, and on irregular margins on the ground truth class. These enable reducing intra-class distance while enlarging inter-class distance. The paper interprets this as a distance penalty margin on a normalized hypersphere, hence the name arcface. Specifically, the loss function is defined as the followed. The deep patent dataset consists of approximately 350,000 drawings collected from US design patents. Since design patents protect the visual form of objects, their drawings are high quality and diverse in shapes, making them suitable for image retrieval training. The dataset is divided into training, validation, and test sets, serving as a standard benchmark for model evaluation. Deep patent reflects the unique challenge of patent drawing, such as black and white images and multiple perspective views, unlike the others' nature image datasets. The triplet methods use only one positive and one negative at a time, making negative utilization inefficient and limiting its effectiveness for large-scale patent image retrieval. InfoNCE can simultaneously learn from many negatives within a batch, alleviating triplets' limitations and showing stable performance in self-supervised learning. ArcFace, as a classification-based learning model, has a simple framework while enhancing both intra-class compactness and inter-class probability, thus providing the strongest metric learning performance. Based on experimental research, this paper adopts InfoNCE and ArcFaces as the core learning method, while using triplet as a baseline for comparison. The dependent dataset was used and the trained validation test. Please follow the original dependent paper. All networks are implemented using the PyTorch metric learning library with EfficientNet B0, VITB, and SwimB and SwimV2B as backbones. Backbones means like image encoder. Preprocessing included grayscale conversion, resizing, and center crop, with input channel set to 1 considering the black and white natures of drawings. Since patent drawings often have large white margins, OpenCV was used to crop them off. Training was configured with a batch size of 256 automizers and an initial learning rate of E4. A patent drawing retrieval was conducted using the architecture shown in Figure 2. Curry images and DB images are embedded into 512-dimensional vectors through the same backbone network and embedding module. The FICE library was used to implement efficient similarity searches of embedding vectors. FICE is optimized for fast KNN neighbors searches and large-scale datasets. The train validation test split was the same as that of the patents, and training and retrieval were separated, and no identical images were included in both query and DB sets. The retrieval system's performance is evaluated using mean average precisions, and MAP is calculated as the mean of average precisions computed for each query. Accuracy measurements was implemented using the accuracy calculator from the PyTorch library. The proposed methods achieve a 0.477 improvement in MAP compared with the deep patent paper, establishing a SOTA. Specifically, the best results were obtained when combining the SwimV2 backbone with R-phase metric learning and suitable data augmentation. The performance is presented on Table 2. Conventional image descriptor methods such as RILBP fail to effectively handle this task. In the comparison of learning methods, triplets show the lowest performance. InfoNC improved upon it, but ArcFace achieved the best results. A triplet was less efficient due to limited use of negative samples, whereas InfoNC leveraged many negatives within a batch, resulting in performance gains. As you can check at Table 3, the backbone compositions Swing V2 is the best performances backbones model. Efficient nets as a lightweight model provide baseline performance but fail to capture complex pattern drawing representation. The swing transformer family captures fine-grained structures with an image through hierarchical self-attentions, with Swin V2 achieving the highest performance. Swin V2B was less prone to overfitting than Swin V2L model, providing more suitable performance and being considered the optimal choice. In Table 4, Swin V23 224 by 224 model is yielded the lowest performance within an MMP of 0.638. 256 by 256 achieve MAP of 0.767, providing stable performance due to the characteristic of deep patent datasets. Since more datasets were larger than 1000 by 1000, cropping to smaller sizes results in the loss of essential retrieval information. In experiments comparing augmentation methods with the Swin V2B backbone, random crop proved to be the most effective. Weak augmentations like Gaussian blur and reference in SimCLR V2 and Moko V3 didn't show significant improvements in this study. As shown in Figure 3-A, a small number of successful retrieval cases were observed even with the proposed method. One possible reason is insufficient database size, and retrieval quality tend to be deteriorated in the case of simple shapes like round shape. A similar failure case with simple shapes was also reported in the previous work, suggesting that this is an inherent problem. As you can see at figure 3, the proposed message is captured more similar images than triplet model, which is the conventional method. The proposed methods achieve new SOTA in both MMP-based quantitative and qualitative evaluations, significantly improving the accuracy of patent drawing retrieval. The architecture combining transformer and metric learning significantly outperformed conventional search method. The work provides the practical solutions to the long-standing problem of patent drawing retrieval. Uh, However, this studies was based on deep patents, but performance on large datasets remains untested. Future work will investigate whether convergence and practical level performance can be achieved. Retrieval quality deteriorates for simple shapes like round shape, indicating limitations related to database size and representations learning. Thank you for listening.